Today I'm going to talk about the design and the control of a quadruped robot, Panther, for highly dynamic motions. My name is Yanran. I'm from UIUC Mechanical Department. I'm very happy to join this virtual seminar session. So our inspiration comes from nature. So in this video, hopefully you can see a snow leopard chasing a mountain goat down on a very steep cliff. So this demonstrates that quadruped animals has very highly dynamic capability to traverse very complex terrains, and we want to somehow duplicate these behaviors. In this talk, I'm going to touch upon three aspects, the design, planning, and control a little bit without introducing on the perception, even though it's very important. So there are many high-quality quadruped platform has been developed over the years. On the first row, you can see the MIT Cheetah family, and on the bottom row, you can see other well-designed quadruped robot platforms, including Animal and AlienGo, Mini Tower, HiQ, which is a hydraulically actuated quadruped robot. So many work has been done in this area for highly dynamic motions, and we want to customize our own platform so that we can achieve the result that we want. That is not limited by the hardware limitation. So first, I'm going to talk a little bit about the design of a robot leg, because in order to have a quadruped robot, we need to design a robot leg that's capable of highly dynamic motions. And in order to design a robot, in general, there are many parameters that need to be determined along the way, including both mechanical as well as control parameters. On the mechanical design side, we have to not only choose the motors, but also we need to also choose the gear ratio. So traditional methods treat mechanical and the control design in a sequential way, where the specification of the hardware is fed into the control design process as a constraint. So in the control design, we design the signal based on these constraints to maximize some metric. However, we want to simultaneously determine the important mechanical design parameters as well as the control signal. So we want to explore in the way of hardware and software co-design. We do this by first determining which actuator to choose. Since we want to design a small-scaled robot, we use the specific power as our criteria. Specific power is basically the ratio between the maximum power divided by the weight of the actuator. So on the left-hand side, you can see the figure of gap radius versus the specific torque. Specific torque has been widely used in the design of electric robot, but it's more significant for large robot because of the long linkage length. So in order to generate the same ground reaction force, it requires higher torque. However, for our case, we want to design smaller robot, so specific power is a more reasonable metric for us to use. And we plot the data for the motors from 3 companies, and the Parker motor could satisfy our requirements. So once we have determined the actuator itself, we want to also be able to determine the gear ratio. It is very important parameter to choose because there's a wide spectrum of gear ratio for leg robot. So on the low end, we have a Mini Tower robot, which has 1-to-1 gear ratio. It has a direct drive, which basically means there's no transmission between the motor itself and the linkage. This design is highly back-drivable. However, it has really low torque output, and because it's operating constantly at the low speed regime, it dissipates a lot of heat, which results in low energy efficiency. On the other end of the spectrum, we have a high gear ratio robot, Animal, for example. It uses a series elastic actuators. So it uses high gear ratio together with stiff spring and a force sensor to realize variable mechanical impedance. However, because of this design, it limits the force control bandwidth, which is very critical for high-speed dynamic motions, local motions. So we want to take the third approach, which is the proprioceptive actuator design. It combines an electric motor with a moderate gear ratio, which guarantees back drivability but has higher torque output compared with direct drive. And the problem that we want to solve is to use the optimization to guide us in the gear ratio selection. So in order to find the gear ratio, we use a simple model. On the left-hand side, we can see that the robot is assumed to be a point mass robot with a negligible linkage length, and the rotor inertias are lumped at the two joints, the hip and knee joints. And then we mount the robot on a vertically installed linear rail, so the robot can only move up and down. And we parameterize the ground direction force by Bezier polynomial. So we want to calculate the impact force upon touchdown, and we use the impact model as shown here, which says the change of momentum is due to the impact force imparted by the ground and the linear rail. And we also have other constraints to say that the foot does not slip and the base does not deviate from the linear rail. And by solving this linear system, we can get the impact force. And then we can formulate a general nonlinear program with the objective of the ratio of the maximum jumping height and the norm of the impact force. Because we want to maximize the jumping height while minimizing the impact force to protect the transmission. The constraints that need to be satisfied include forward kinematics, differential kinematics, impact model, the torque mapping, and the inequalities for the joint angle, joint angular velocity, and joint torque. So by solving this NLP, we can get a locally optimal solution. We get the gear ratio around 23:1, and at the same time, we have the optimal ground reaction force for the jumping performance. So once we have the motor selected as well as the gear ratio determined, we went ahead to synthesize the robot. So each leg of the robot has 3 joints, the abduction-adduction joint, the hip joint, and the knee joint. So since the linkages are made of lightweight materials such as 3D printed plastic and carbon fiber, the total link weight is less than 10% of the total weight of the leg module. So here is a explosive view of the hip motor module. You can see that we use a 2-stage compound planetary gearbox design to achieve relatively high gear ratio in a very compact space. So we went ahead and assembled the robot leg and mounted on a linear rail and do the vertical jumping test. And we can achieve a maximum jumping height of 0.62 meters, which is 2.4 times of the leg length. A force plate is placed beneath the platform to measure the ground truth of the ground reaction force. Okay, once we have the leg module, we then assemble the full quadruped robot. So by using the same model, we can also compute the optimal control input for a maximum jumping performance. In this case, it could reach 0.7 meters high. And a simple projective programming based stabilizing controller is used here to stabilize the orientation of the robot so that we can achieve a very stable landing behavior. So once we have this quadruped robot, we can use it as the hardware platform for further research on path planning and control. So now I'm going to shift gears to talk about the kinodynamic motion planning. So the goal here is to generate dynamic motions for multi-legged robot to traverse very challenging terrain. So here we use a planar 2D robot with 2 legs, and we assume the robot traverses the terrain using jumping motions, which consist of stance phase as well as the aerial phase. So this problem could be formulated as an optimization with the objective to minimize the state at the end of the motion and the goal state. And the following constraints has to be satisfied, including the robot dynamics, the foothold choice, and so on. And this problem in general is a hard problem to solve because there's non-convexity coming from the robot dynamics and the torque limit constraint. So as you can see, the Jacobian is used here in this constraint, which has the sine and cosine terms, which is non-convex. In addition to that, we have also need to consider the context sequencing of the robot because it has two legs, so it can touch down in different ways. So this problem in general is hard because of the combinatorial nature of it. So in order to condense the constraints, we use the notion of feasible range polytope. It is the intersection of the contact range cone and the actuation range polytope. So CWC is basically the friction cone and AWP is the constraint imparted by the actuators. So the feasible range polytope of one leg has the force term as well as the moment term. And the FWP of two legs is the Minkowski sum of the FWP at each leg that is in contact with the ground, where the Minkowski sum of two sets is defined in the following way. So here is a visualization of the feasible range polytope for this planar robot. As you can see on the lower left side, the FWP of each leg is a two-dimensional polytope, which means that when the robot is in single stance, the robot can only apply wrench in this specific direction. This has encoded the information that there's a coupling between the translational and the rotational dynamics of the robot. On the right-hand side, we can see that when the robot is in double stance, the FWP is a three-dimensional polytope, which has a higher control authority. So by using the notion of feasible range polytope, we can transcribe the original problem into a more compact form. So in the original problem, we have a complex dynamics because of the bilinear term R cross F in the dynamics equation. And we also have very complex constraints, which includes the force has to be within the friction cone and the torque has to be within the torque limit. Because of the Jacobian matrix that I talked before, this constraint is non-convex. However, in our if we use FWP, we can simply use a linear dynamics model because we operate directly on the spatial range regime, and we have a more condensed constraint. However, this constraint is still non-convex and nonlinear, so it's a still very complex constraint. But we can use mixed integer relaxation to formulate a mixed integer convex program, which could be solved efficiently. So we do this by first discretizing the configuration space of the robot. So on the left-hand side, you can see the C space of the robot is having a really non-convex shape because it has to satisfy some kinematic constraints to prevent the robot from hitting the ground. We discretize the C space into tetrahedrons, and each tetrahedron could be expressed as a set of linear inequality constraints. By making the following assumptions, which says the legs are massless, and when the robot is in double stance, the stance width is always equal to the body length, and the robot prefers double stance to single stance whenever possible. By making these assumptions, we can segment the C space into three regions, and each region corresponds to a stance mode. So for example, the red region corresponds to the back stance, the black region, double stance, and the blue region, the front stance. So by making these assumptions and segmenting the C space, we can have a one-to-one relationship between the configuration of the robot and its stance mode. This implies that the context scheduling is baked into the search for the state trajectory Q of t. This is significant because we have drastically reduced the number of optimization variables in the MICP. As well known, mixed integer program is having the problem of a curse of dimensionality, which means as the number of optimization variable increases, the problem takes exponentially longer time to solve. So reducing the number of optimization variable is actually quite important. So once we have discretized the configuration space, we can make the originally non-convex range constraint a mixed integer convex constraint. So we do it by assigning a binary variable to each cell of the C space and then construct a binary matrix B. And when ij's entry of the matrix is equal to 1, the following constraints are activated. The first one says the configuration of the robot at time ti resides within the cell J. And when the configuration resides within the cell J, then the set of constraints correspond to the FWP constraint with this cell is activated. So the implies operator is implemented using the big M formulation. And additional constraints have to be imposed for physical feasibility. Specifically, the summation of the B matrix along the J direction is always equal to 1, which means that the configuration at any time ti could only reside within one of the cells. So this MICP could be solved by solver Groovy to attain very complex behaviors. So in this case, the robot wants to reach the goal region on the right-hand side. However, due to the torque limit constraint, it cannot do so in a single jump. However, it can explore the feature of the terrain, which it uses the platform on the left-hand side as a stepping stone to make 2 consecutive jumps to reach the goal region. So we think that one of the potential application of the mixed integer algorithm proposed here is to generate a trajectory to warm start a full-scale trajectory optimization, which is previously hard to obtain this motion on a single shot because it requires a behavior that is not suitable for gradient-based method. Okay, so the last part of my talk concerns about the model predict control on the robot. So we assume the robot to be a single rigid body. So we neglect the leg masses. So we have a dynamics for the single rigid body. And the orientation representation that's being widely used for quadruped robot is Euler angles. However, it has the singularity issue, which is also known as the gimbal lock. So when the 2 or more axes of the rotation are collinear, this matrix becomes singular and it has some issues. To solve this problem, quaternion has been introduced, but quaternion double covers the SO3 manifold, which means that for each orientation, there are 2 different quaternions correspond to that. It has some problems as well. For reactive controllers, it is okay because sine functions, for example, could be used to switch between local charts. However, this behavior is not desirable for predictive controllers such as MPC. So we want to directly work on the rotation matrix and formulate a representation-free model predictive control. We do this by using the variation-based linearization on the rotation matrix. For the rotational dynamics, we have this highly nonlinear term because the rotation matrix evolves on this SO3 manifold. And we linearize the dynamics around the current point of the orientation ROP by taking the variation delta R around within the tangent space located at the ROP. Then we use delta R to approximate the distance between 2 points on the SO3 manifold. We take the Taylor expansion of the matrix exponential map and have this linear relationship. The variation of the angular velocity is similarly defined. Once we have the expression of Rk and omega k, we can plug them back into the original rotational dynamics to obtain a linear dynamics. However, this linear dynamics has variables with matrices, which is not very friendly to the MPC formulation because it requires vectors. So we have this vectorization scheme to transcribe it into a linear dynamics with vectors, and then we use a forward Euler integration to get the final discrete time affine dynamics. So once we have the affine dynamics, we need to also make sure the cost function is in quadratic form. The original arrow function for the orientation uses the matrix log function. However, it's not a linear in terms of the optimization variable, so we use a configuration arrow function presented here to approximate that. So on the right-hand side, we can see that the original cost function is a convex shape. But simply using the Euler map has singularity issues, and using the V map, it does not cover the whole space from negative pi to pi. However, the configuration error function could capture the basic shape of the original cost map. So now we have all the components needed for the MPC. We have a quadratic cost function, discrete affine dynamics, and the linear state and control constraint. Then we can transcribe this MPC problem into the standard quadratic program and solve it by QP solvers. So here's a control system overview. We have a user input fed into the finite state machine, which sends the desired state and the control trajectory into MPC, which in turn formulates a QP for the QP solver and solve for the ground reaction force when the leg is in contact. And when the leg is in swing, the swing controller takes over, and the robot is interacting with the environment, and the sensor signals goes back into the main control loop through a state estimator.